In this video, we will consider few examples of closed sets. So consider the set A capital A equal to set 1 by n element of n. It means capital A equal to 1, 1 by 2, 1 by 3, 1 by 4, etc. Now we show that each point of capital A is isolated. So we choose an arbitrary element 1 by n element of capital A and we choose epsilon equal to 1 by n minus 1 by n plus 1. Then we consider the epsilon neighborhood V epsilon 1 by n intersection A and we can see that which is equal to set 1 by n. It means the epsilon neighborhood is intersecting A at only the point 1 by n and it is not intersecting capital A at any other points. Therefore, by definition, we can get that 1 by n is not the limit point of capital A. So, every point in capital A is not a limit point of capital A. Therefore, every point of capital A is isolated. Now, we try to find the limit points of this set and we can see that 0 is the only limit point of this set because every neighborhood at A centered at 0, it will contain some points of A. Hence, 0 is the only limit point of capital A and 0 is not an element of this set. Therefore, A is not closed. Now, we are trying to construct another set capital F equal to A union set 0. What we are doing is we are trying to add the limit points of the set to it and make another set so that it becomes a closed set. So this is a closed set and this F is called the closure of A. Okay, now we'll go to the next example. Here we discuss about the closed interval CD. Now we show that this closed interval CD is a closed set. So let X be a limit point of closed interval CD. Then by definition of limit point, there exists a sequence Xn in closed interval CD and the sequence Xn converges to X. Now we have to show that X belongs to closed interval CD. So since Xn lies between X and T, we have a previous result. Using that we get that X also lies between C and D. It means X element of closed interval CD. Therefore, closed interval CD is closed. Okay, now we will go to the next example, example number 3. Here we consider the set Q of rational numbers as a subset of R. Now we want to find the limit points of Q. So we actually get that every point of R is a limit point of Q. So for that we let Y element of R be an arbitrary number. Now we consider an epsilon neighborhood V epsilon Y. It will be open interval Y minus epsilon Y plus epsilon. Now this epsilon neighborhood will always contain some rational number other than Y. So we take that rational number as R and R it will be different from Y and there exists a rational number satisfying this condition in this interval. So V epsilon Y, it will intersect Q in some other point other than Y. Therefore, this Y is a limit point of Q. Since Y is an arbitrary point of R, Y, every point of R is a limit point of Q. Therefore, Q dash will be equal to R. And therefore, Q closure will be also equal to R. Okay, thank you.